We want to begin our evening together with a solid foundation on the state of the Palouse Basin. There's no better person we can think of than Steve Robischon to do that. While he's a man of great humility and quiet, I'll say for sure he's brilliant. He also knows water like few others. And I'll also say that he has this dry, wonderful sense of humor that I think makes people gravitate to him quickly. He's a great team player. He is the executive director of the Palouse Basin Aquifer Committee, and he would have you know that he grew up in Butte, Montana. He has owned and driven the same car for the last 24 years, and he used to be taller. Steve Robischon.
Thanks, Tom. Thanks, everyone, for coming today. One of my strategies, I don't really like standing up in front of people, especially when they're all staring at me. So one of my strategies is to fill my presentations with lots and lots of slides so that you'll look over there and not look over here. And I'll just narrate these things as we go through. I like to start these things with a water joke. In the past, I've received some less than favorable feedback on some of my water jokes from someone whose name will go unspoken. But I'm going to carry on and keep going with the water jokes because I like the water jokes. So here's an introductory water joke for you. Why do sharks swim in salt water? This is about the standard response I get for my water jokes, so maybe that's why some of the feedback that I get is less than favorable. Okay, I'm going to talk about three different things. I'm going to go through a whole bunch of stuff really quickly. I'm going to talk about water use, which is pumping. I'm going to talk about groundwater levels, and I'm going to talk about some of the projects PBAC is involved in. As a reference, most of you should have one of these. There were some of these out on the table when you came in. If you want to learn more about what I'm talking about today, a lot of it's in this document. If you ever have questions or would like to talk to someone or to hear more about what's going on in the basin, you can contact any of these folks who are the PBAC representatives or the administrative representatives from the state agencies or me. If you want to find those numbers in those emails somewhere, you can go out to the website that we have. That's the address of the website, or you can just Google Palouse Basin Aquifer Committee and find that address. So there's a lot of places you can get more information if you need it. So I'm going to fly through some of this, so don't have to try to remember and memorize everything I'm going to do. Water use. 2011, there were 2.6 billion gallons of water pumped by the municipal entities on the Palouse Basin. 2.6 billion is a really big number, but what does it mean? If you were to go down to Lewiston and build a building that had a footprint that was equivalent to 4 football fields kind of placed next to each other, and then you built that building all the way up to the top of the Lewiston grade and you filled it with water, that's about 2.6 billion gallons. So that's a lot of water. You can see how it breaks down here. Pullman and Moscow each pump about a third of the total, and the rest of it breaks down by the universities and the smaller municipalities. How does 2011 fare against 2010? In a lot of these charts, the red bars mean more water use or drier or hotter. The blue bars mean less water use or cooler or wetter. So in general, not politically speaking or anything, red is bad and blue is good in a lot of these charts, okay? 2011, the water use was up 3.1% from 2010. And this chart breaks it down by pumping entity, how their water use compared in 2011 from 2010. How about 2011 versus 1992? 1992 is when the groundwater management plan was enacted, which is the plan that we use here to try to help manage the water. Since 1992, the total pumping has gone down almost 16%. That's down 16%. Since that time, the population on the Palouse has gone up like 17%. So the pumping's gone down, the population's gone up. Pullman, you can see, has a little bit of a red bar there, but the population in Pullman I looked at yesterday, it's up 30% from what it was in 1992. So there's a lot more people living in Pullman than there were back then. Baseline and non-baseline. This is an example of pumping by month, and you can see that in the summertime, folks generally tend to pump more because they're irrigating outdoor stuff. So what you can do is you can draw a line across basically the November, December, January, February pumping. That's kind of the stuff that's indoors because people aren't using water outdoors during those months. And you can call that baseline. And then the stuff that happens during the irrigation season is mainly outdoor water, and you can call that non-baseline. So these next few charts break it out between baseline and non-baseline. 2011, the non-baseline water use, that's kind of the outdoor water use as a percentage of the total, is broken out here by entity. And you can see that the lowest percentage was for UI, and also amazingly the highest percentage was for UI. And the reason for this is UI uses reclaimed wastewater to irrigate a lot of their green space during the summer. So if you count the reclaimed wastewater that they used, they would have been pumping 45% of their total during the summer. But since that reclaimed wastewater isn't water that's being pumped out of our aquifer, not fresh potable water, the actual amount that they actually pump out of the aquifer system is only 22%. And you can see how it breaks down by entities in between those two extremes. Okay, what's the difference between 2010 and 2011 in terms of baseline? So this is indoor water use, 2011 versus 2010. And you can see that it varies from minus 2.5% or less indoor water use up to plus 7.5%. How about non-baseline? This is outdoor water use, 2011 versus 2010. And you can see that, again, that it varies from 8.1% less outdoor water use to 17.5% more water use. Okay, a lot of the outdoor water use kind of depends on the weather. When it's hot and it's dry, people use more water outdoors. They water their lawns more frequently, keep their plants wetter. These three charts kind of describe the climate in the 2011 and 2012 irrigation seasons. And I know it's kind of a push calling April the irrigation season around here, but that's kind of a standard thing in places to start counting April as irrigation season. So what you can see, this top one is temperature, and this is a comparison to the recent average. 2011, all of us that were here remember that it wasn't a really very good summer. It was a cool summer. 2012 hasn't really been that good a summer until the last month, or this month here, which isn't complete yet. So you can see we had kind of a cooler irrigation season. We had a wetter early irrigation season in 2011 than we did this year. This bottom one is evapotranspiration, which is kind of a measure of how much water the plants need. So in 2011, we really the plants weren't really requiring nearly as much water as on average. And again, in 2012, we were similar, but a little bit, you can see a little bit more water use required in 2012 than 2011. So if you just look at these two charts, you might be able to guess that in 2012, we're using a little bit more water than we were in 2011. Just kind of matching the blues and the reds. You'd say, well, maybe 2012 is up a little bit from 2011. So here is a very, very busy chart that shows the monthly pumping 2012 versus 2011 for each one of the entities. So for example, here's, well, I'll show you. This is Palouse. So in January, Palouse pumped a lot less than they average do. In February, they pumped less. By the time we got out here to May, Palouse pumped a lot more than they usually do. So you can see that these bars go kind of up and down erratically during the course of the year so far, but something was going on in May where all of the entities pumped more in 2012 than they did in 2011. So what might have made the difference there? Well, of course, it's weather. It's weather. That's why people use water outdoors. So if you look at 2011 in May, we had 2.4 inches more precipitation than usual. In 2012 in May, we had 0.8 of an inch less. So there's 3.2 inches of rain difference between 2012 and 2011, and you see it in the pumping. So a lot of the summertime pumping, which is a big chunk of the total, is basically based upon what the weather is year to year. So when you see the relatively small percentage changes year to year in total pumping, A lot of it is tied to the weather. It's not tied to drastic demographic changes year to year. Okay, this is another busy one that shows the cumulative change. So what this is a running total. So Palouse started out really well, and they started pumping a little bit more, and a little bit more, and a little bit more, and by the time they got out here, they're right up about average. So this is a running total of pumping versus what they pumped last year. If you look at the total so far this year, pumping's up 2.7% from last year. Again, a little bit warmer, a little bit drier. Probably most of that is weather related. Okay, this is a chart of temperature and precipitation out at the airport. The top one is temperature. It shows the extremes and the average band. The bottom one is precipitation. When I first saw this precipitation chart, I thought, well, the gauge must be broken. Somebody needs to go out there and tap on that gauge because it looks like it's obviously stuck at 15.71. But when you think about it, what that is we haven't had any measurable precipitation out at the airport since the middle of July. So it's been really dry since the middle of July. And I thought, well, that's going to make 2012 look a lot worse than 2011. So I went back and I looked at 2011, and geez, look at that. It got dry in early June in 2011. So it started earlier last year. If you kind of match the 2 years up, you can see that this past year we had a big chunk of rain in the later spring, and we kind of kept getting a little bit more rain out into July. Last year, we went dry earlier. And so last year, we ended up a little bit above normal at 18.42 inches. This year, it looks like we're headed to be above normal, but who knows when it's going to start raining again. Okay, that's pumping. Water levels. There's a monitoring well at the WSU test well. This is down by the power plant in Pullman on WSU campus. This is the well that we have the longest water level record for. It goes back to 1935, I think it is. This chart shows the water level versus time. So back in 1934, the water was at 2,342 feet above sea level. In 2012, it's about 2,242 feet above sea level. So you can see it's gone down about 100 feet. The green line is the average decline of water level throughout the period, and it's 1.3 feet per year. The red line out here is the average decline since 1992, which is when the groundwater management plan went into effect. And you can see that the average decline is now around 0.9 feet per year. So the water levels are continuing to go down. They're not going down as drastically as they were before, but they're continuing to go down in the lower aquifer. This is the lower aquifer where we get most of our water. If you zoom into the short term a little more, you can see, again, what I try to do when I look at these things is I look at the highest the water gets in a given year, and then I go to the previous year and I look at the highest the water got in the previous year. So you can see the difference between this year and last year is somewhere less than a foot. The difference between last year and the year before is somewhere less than a foot. So as you trace your way back, you can pretty much see that it's somewhere less than a foot a year that the lower aquifer is going down. This is the Department of Ecology Pullman test well out on Sunshine Road, so it's about halfway between Pullman and Moscow. Here is the chart for about the last 7 years for that well. Again, if you look at year to year, you see maximum to maximum less than a foot, maximum to maximum less than a foot. You're getting the same kind of general decline there. This is a well that's about a half mile north of here, funded by the Department of Water Resources in Idaho. It's a deeper well, Grand Ron well. And this is the chart for that one over the past several years. Now this one looks different than the two previous ones, and that's because that well is close to some of the major pumping wells in Moscow. And so when the major pumping wells turn on, the water levels go down, which is what this yellow line is. And then when the big wells turn off, the water levels come back up. So that's why you see these jagged marks. Again, it's about a foot a year. Okay, the upper aquifer. This is a picture of the water department building, this building that you see out here on the north end of Moscow. This is where the two upper aquifer wells in Moscow are, Moscow 2 and Moscow 3. This is a long-term chart of the water levels in Moscow Well 2, goes back to 1938. What you see here is a general declining trend that is reversed and comes back up to the top here. Back in before the late 1950s, both UI and Moscow pumped solely from the upper aquifer, and people became quite concerned about the water level declines here. And in addition, the upper aquifer water quality isn't quite as good as the lower aquifer water quality, so folks kind of wanted to have a little improvement in their water quality, so they drilled wells into the lower aquifer about this time. And when they did that, they were able to take pressure off the pumping on the upper aquifer, and sure enough, the upper aquifer recovered. And so this is really a good sign about the upper aquifer, because it tells you that if you don't pump it too hard, the water levels will come back. There is a sustainable level of pumping in that aquifer. Unfortunately, back then, we were pumping it too hard and the water levels were not stable. If I look at what the pumping was like back then versus now, this is the pumping, the blue bars, and this is the pumping now. This is that same water level chart you saw in the previous thing. You can see that the pumping went down drastically when they drilled the deep wells, and sure enough, the water levels came back. But what we're finding here is we're beginning to learn lessons out here, which is the present, that we learned way back here in the 1950s. And those lessons are that if you pump too much water out of the upper aquifer, the water levels go down. You know, not too brilliant requirement to figure that one out. But over the past year in Moscow, at least 5 wells on the north end of town have gone dry. The shallower wells, that are the older wells, hadn't been drilled as deep because they didn't need to get drilled as deep when they were old. They've gone dry because our water levels are going down. So I hope we're learning the lesson that if we pump it too hard, the water levels go down. If we don't pump it too hard, the water levels come back in the upper aquifer. IDWR1, this is again down, or about a half mile north of here. This is a shallower well. It's above the basalt in the upper aquifer. And you can see that this thing has kind of a strange curve to it. Sometimes it goes up, sometimes it doesn't. It's closer to the surface, so it's influenced more by what's going on at the surface. So if I look at the climate chart for the last 3 years, I see that during November, December, January, February, March of 2009 and 10, it was a lot drier than normal. And here I see, looking at the well's water level didn't come up that year. If I go to the next year, I see, oh, we've got a wet year here, and sure enough, water levels came up really well that year. Again, we had another wet year this year, and again, the water levels came up. So these shallower wells respond to the precipitation much more quickly than the deeper wells. The water's getting to those, the pressure's getting to those more quickly. This is IDWR3, which is at the same location up north of town, about a half mile from here. This one is in the upper aquifer, but it's further down in the upper aquifer in what's called the vantage sediments. And this is where the city's upper aquifer wells get their water, in the sediments below the basalt in the upper aquifer. This one you can see kind of that same troubling decline where it may be that we're pumping the upper aquifer a little bit harder than it can respond to. And so this last summer we've been pumping a lot harder because one of Moscow's deeper wells has been taken out of service to get the pump and the motor serviced. So in order to make up for the water that they're not pumping out of the deeper aquifer, they've been pumping the shallow aquifer as hard as they can. And when you pump the shallow aquifer as hard as you can see what happens to the water levels. This is the climate chart for that one. Again, you see not so much response difference from year to year. Really dry year, it went up about 2.5 feet. Pretty wet year, it went up about 3.5 feet. Not a lot of difference like we saw in that shallower well. Okay, zoom in on the short term. This is what I want to call attention to. This is this summer when we've been pumping it really hard because we don't have that Moscow Well 9 in service. This well is right out in front of the Moscow Police Department. It's in the sidewalk out in front of the Moscow Police Department. And when you look at the water levels here, you see that right about the time that the well went out, Moscow 9's well went out, and they started pumping the Wanapum really hard, look what happened to the water levels in that well. Just dropping like a rock. So we can't pump that aquifer too hard. Okay, PBEC projects. A couple of these I talked about last year. A couple of them were still ongoing this year, so I'll tell you about that. 2010, I told you about this project we had called the Basin-Wide Aquifer Test. A graduate student was doing it at the University of Idaho under Jim Oginski's advice. What we did is we put these devices in on all of the pumps at the major entities so we could figure out when the pumps were turning on and going off. We put these devices in a bunch of wells around the basin so we could monitor what happened to the water levels. And when we put those in the wells, we get something that's like kind of an EKG for a well. So we know when the pumps come on and off, and we know what's going on with the wells, and this project was going to try to connect the dots between those two to see whose pumping impacted whose wells. Well, we ran the test for a year, and you can see this is elapsed time. It goes for about a year. These are a bunch of different wells throughout the basin. You can see that during the wintertime, the water levels are pretty stable. People start pumping more in the summer because they're irrigating and the water levels go down. Then they tail off on the pumping, water levels come back up, but they don't make it back up as far as they did the previous year. So that's that decline that you see every year. So we continued this project with another student. Now we have 2 years worth of data, and you can see 2 summertime drawdowns here. And you can see these lines, which are the kind of straight line decline that's measured out of those things. And you can see that most of these wells, or all of these wells really, have pretty similar water level declines. So that would lead you to believe that maybe these wells are all in the same basin. They're all over the long term kind of behaving the same. One of the things that you kind of see over in Palouse, which is this, is these other wells, they kind of come back during the fall and early winter. Palouse just kind of keeps going down a little bit. So you can see these are headed upward here. This one's headed downward. So that's something that we still want to learn more about, is just how quickly or how tightly connected Palouse is to the rest of the Palouse Basin. One of the things that the student who did the second year of the test did was he looked at which wells responded to pumping in which pumps. And from that he concluded that there are a bunch of compartments in the lower aquifer. And these compartments aren't like waterproof or watertight compartments. So the water can move between the compartments, but it takes it more time and it happens more slowly. So over the long term, all of these wells are going down around a foot a year. But if I turn a pump on over here, I'm not going to see it in a well over here. So that's how he determined what these compartments were. And there's a lot of geology behind this that we still need to learn a lot about. But that's the latest thinking about the lower aquifer, is that it's compartmentalized, and it's not just one big bathtub. It's got a bunch of different compartments in it. Again, the compartments are all connected over the long term, but not over the short term. Tritium study. Turns out there was hardly any tritium in the air before nuclear weapons testing in World War II. And so anything that we find that has tritium in it probably happened after World War II. So we can draw this line and say, if there's no tritium, there's no young water, if there's no tritium present. If there is tritium present, there's young water present, right? At least 60 years or younger. And so one of the students at the University of Idaho did a project where she did a lot of sampling in wells for tritium and came up with this result. So what this shows is this level here is the level of detection of tritium. So anything to the left of that line, no tritium was found, and so there was really no young water found in those wells. Anything to the right of that line, they found tritium in, which means there is some young water in those wells. This axis here is the depth of the well. The blue symbols are all for the upper aquifer wells, and the red symbols are for the lower aquifer wells. And lo and behold, what this project found was there were only a couple of instances where they found young water in the lower aquifer. And so what that tells us is it's taking a long time for the water to get into the lower aquifer. The upper aquifer, we see a lot of the wells that do show evidence of tritium. So young water is able to get into the upper aquifer, so that upper aquifer will recover a lot more quickly than the lower aquifer will. Again, there are wells really close to the surface. This well is less than 100 feet deep, and they didn't find any tritium in it. So there are wells in the upper aquifer that don't see the water for a long time either. And that's just the nature of the geology. It's just so complicated that we can't draw any conclusions about how it's like a nice flat layer cake. So that's what we learned from that study. Department of Ecology gave us a grant of $350,000 this past year to drill some monitoring wells away from the major pumping centers so we can kind of see what's going out around more of the edges of the basin. 2 of those are done now. This one is at Ewardsville Grange. You can see the Grange is back there. There's the rig. Here's another picture of the rig. There's a second one on Wilbur Creek on Flat Road. There's another picture of the rig out there. This is about 2 weeks ago that this was happening. They've got 2 more wells that they want to drill on this, and then possibly, if the funds work out right, we'll drill another 2 wells for a total of 6 wells. So we'll have a lot of information out kind of on the edges of the basin about what the water levels are doing out there and how they respond to pumping inside the basin. Okay, so that's it. That's pumping, water levels, and projects. Usually at the end of my presentations, I like to do this joke with the water witcher guy. But again, I've received some negative feedback from someone whose name will go unmentioned. But I'm still not giving up on the water jokes. So here is another water joke to end my talk. Hey, could you pass that bottle of water? Why, yes, I could. Is that one better? Okay, thank you.
Any of you who would like to ask a question, if you wouldn't mind stepping to the center aisle and sharing that so that it can be recorded. Any questions for Steve?
I'm just curious as to whether or not the water level rose in the well that was not being pumped due to the pump being down.
That's a good question, and someone asked me that last week, and actually the water level hasn't really risen in that well. But in general, this time of year, when you see what happens in the summer, the water level is generally going down in the summer. And so now the water level isn't going down, it's kind of staying constant. So that may be a combination of summertime pumping, but recovery in that well. So the water level hasn't really come up in that well since the pump's been down. I always get scared when ex-deans start asking questions.
I wouldn't worry about it if I was you. In oil fields, oftentimes, you can actually damage an aquifer by overpumping it. And like in the Vantage Sand, if you collapse it just by pulling out enough water, maybe you aren't going to be able to get the water back in. Is there any concern about that the upper aquifer, which is not that big of a deal for us, but it is a deal, when we do these kinds of pumping things, when we have these emergencies, you could be doing damage to it?
I'm not an expert in this, and so I'm not going to be able to give you a good answer. And if there are any experts out there that can give you a good answer, I'd like to hear what it is. But I think that since we've been pumping Moscow Well 2 and 3 since the 1930s, I think already we've done some damage to that part of the aquifer, because you can see you can't pump as much out of it as you used to and have the water levels go down. But again, the Wanapum, the upper aquifer, is compartmentalized too, so there may be other areas of the Wanapum that are accessible with sustainable water. So it's a good question. I don't have the exact answer for you.
Quick question on your tritium. Does tritium exist underground in a state where it could be picked up by deep wells and not be the result of young water?
I don't think that it does. And is Kent still here? Kent's an expert. Maybe he can yell the answer to that one.
That's what.
Kent said he can't think of a mechanism that would give you tritium in water that wasn't from young water. So chances are if tritium's there, there's young water there.
Yes, sir.
Why is the water quality in the Wanapum poorer than the deep aquifer?
It's a lot harder. There are a lot of minerals in it, and so that's why folks sinks used to stain, and they got water softeners because it's closer to where the erosion was occurring, and so I think there's been a lot more chemical activity going on in the upper aquifer. It's not a bacteriological problem, it's a mineral problem.
Steve, thank you very much.
You're welcome.
One more question.
One more question. The tritium correlation was really interesting, and so I don't know a lot about this, and I work with educators, and we go into classrooms and teach about this. And my question is, has there ever been any information that you're aware of about tritium we teach about natural filters, and so what I'm wondering if there ever is a baseline of how deep tritium has been found in the earth anywhere, or is that something that could be naturally filtered once it reaches a certain depth?
I don't know that it's filtered, and again, Kent can weigh in if he wants, but I think that it's basically a description of the pathway. So if you go really deep and the water's able to get there quickly, you may be able to find tritium. If you just drilled a hole and dumped water down the hole, it'll get down there quickly. But if it's taking a long time to get down there, it's not getting down there in 60 years. So I don't know that it is filtered. Kent, again, no filtering?
Thanks.
Kent is the expert out there. Kent Keller from WSU, Professor Keller. Okay.
Thank you
Thanks.
very much, Steve. Inspiring to have that kind of information, isn't it? I feel compelled to be a better steward day to day as a citizen. Thank you so much.